Hello, welcome to episode 13 of Maths in an Empty Classroom with me, Mr. Southern. Today we're going to be looking at the fourth and final example from further kinematics, vectors. And what we're looking at today is this example here, where over the journey of the question we end up with particles colliding. We're going to look at how to deal with that. But first off, let's start off with the information given. We've got that the velocity of a particle p at time t seconds is 3t squared minus 8I plus 5j. And that when t equals 0, the position vector of p with respect to a fixed origin O is 2I minus 4j. And in part A, I'm being asked to find the position vector of p after t seconds. So I've set up on the next page just the key information, so I'm ready to go. I've got that velocity is 3t squared minus 8I plus 5j, and that when t is 0, the position was 2I minus 4j. Right, by now we know that if you have velocity and you want position, you need to integrate, so I'm not going to write that bit down, I'm just going to do it. So I have that r is equal to t cubed minus 8t plus c1I plus 5t plus c2j. Remembering that you get a constant of integration for I and a different constant of integration for j. Now we're told that when t equals 0, what we have is 2I minus 4j. If you substitute t equals 0 in here, you're just going to be left with c1. So therefore c1 equals 2. And if you substitute 0 into here, you're just going to be left with c2. So we've got c2 equals negative 4. Which means that our position vector r is t cubed minus 8t plus 2I plus 5t minus 4j. Meters, this is position. Nice and gentle. Now, what we're told now is a second particle q moves with constant velocity. Now, it's the first time we've met this within this context, constant velocity. So this isn't necessarily calculus. Constant velocity 8I plus 4j. We're given its initial position with respect to the fixed origin is 2I. We're being asked to show that p and q collide. Now what we need to do for this is we need to use the expression for a position vector moving with constant acceleration, which is that the position r is equal to the initial position plus the velocity times time. So constant velocity times by the time it's moving tells you how far it's gone. So we were given that the initial position is 2I and that the velocity is 8I plus 4j. So I'm going to put that into here. The initial position is 2I and the velocity is 8I plus 4j, and that is times by t. Now what I'm going to do is I'm going to write that as an I component and a j component, because what that will do is allow me to compare it directly with this and solve the problem. So I'm going to rewrite this to say that I've got 2 plus 8ti plus 4tj. So this is an expression for the position of particle q. In part A, I worked out an expression for the position of particle p. For these two particles to collide, they must be simultaneously in the same place at the same time. So what I'm going to do is I'm going to say, okay, the I components must be equal. So equating the i's, t cubed minus 8t plus 2 must equal 2 plus 8t. And looking at the j components, 5t minus 4 must equal 4t. So I've said they must have the same I component and the same j component. And what I now need to do is show that that happens for the same value of t. Now, two options here. I could solve one and sub in, or actually these ones look okay. So what I'm going to do with the one on the left hand side, I'm going to subtract the 2 and subtract the 8t to make this equal 0. So I'm going to get t cubed minus 16t equals 0. Factorise out t, which gives me t squared minus 16 equals 0, which actually gives me 3 solutions. T is 0, t is 4, and t is negative 4. I can obviously ignore the t is negative 4 as being negative for time. Now if I solve over here, I get that t equals 4. So I've got a value of t that's consistent, that shows me that when t equals 4, p and q will have the same I component, p and q will have the same j component, which means that they are in the same place and they therefore collide. So I just need to write a little conclusion that says that p and q collide when t equals 4. They simultaneously have the same I component and the same j component, so they must both be in the same place. We could check that. If you substitute in t is 4 to the I component here, you get 34. If you substitute t is 4 into the I component here, you also get 34, so same I. If you substitute t is 4 into the j component of q, you get 16. And if you substitute t equals 4 into the j component of p, you also get 16. So we could write, we don't need to state this as part of the solution, but we could say that the position vector where they collide is 34i plus 16j, because we've shown that that's what's happening. So there we go. Thank you very much.